my high frequency trading, which is like just concurrency to the most, and yeah, I studied as well. The agenda, in particular, is sort of just a random kind of selection of concurrency issues I would like to address. At this point already, like how many people of you have used things like a read-write lock? How many know what volatile is about? Okay, that's good. Yeah, so low-level concurrency on these kind of things, and then we'll take it from there and sort of start with thread pools and discover one contention issue after another, sort of arriving at the architecture that Akka has. What I'm not gonna mention is sort of other threading models, in particular like Clojure's software transactional memory, data flow concurrency, futures, and other high-level kind of things. That's just too much. So to begin with, this entire talk sort of focuses on utilization. So we want to maximize utilization. There's other objectives which you could sort of follow, like low latency or high throughput, but it's sort of a bit fuzzy to distinguish between them anyway, so I'm not going to even bother. The first thing I'd like to get across is synchronization is not the enemy. It's usually contention one way or another. If you think about it like, say, think about junctions on the street, the traffic light obviously creates some contention, but it's usually bad city planning which produces or is the root cause of that contention. And this theme kind of follows us through the whole presentation. Knowing that synchronization is not the enemy, most locking in Java is actually sort of uncontended and also unshared, so not even any other thread tries to do the same thing at the same time, which means that, for example, synchronized is optimized for that case, because that's the usual 95% case. And also another thing is when you're benchmarking applications with synchronized and locks and whatever, it's usually not really realistic because you're sort of provoking contention in your benchmark, which is not really what reality is about. So a bit of detail about synchronized. I said it's optimized for the uncontended case, which means it can be handled entirely within the JVM. There's no operating system call involved whatsoever, and that's just sort of expensive part where you need to stop blocking and you sort of abandon the current execution. How does it work? Mostly compare and set instructions. So for example, I found this old implementation of IBM, which sort of just has lightweight kind of, like in memory there's a few bits reserved at every object, which indicates whether or not someone is holding that lock on that object, or whether it's been locked by your current thread already. And you sort of just mingle around with those bits using compare and switch instructions. If you can't do it sort of within a certain period of time, it resorts back to more heavyweight locking, which is the sort of expensive bit. But again, synchronized by itself is not the expensive kind of part.
So synchronized uses compare and
yeah, initially.
But I thought that there were some Java 1.5 or there was atomic integer and this stuff.
This is that's non-blocking locking. This is what I'm showing here. But even synchronized initially, even if you use a synchronized keyword, it tries to do non-blocking locking like I'm doing it here sort of explicitly. It's just, if it doesn't succeed within a certain amount of time, you can set, I think there are just configuration parameters which you can set, use spinning and these kind of special parameters. If it doesn't succeed within a certain amount of time, it falls back to proper operating system calls, the thing you would expect from synchronized. But it's, as I said, optimized for the uncontended case. And yeah, so that's this sort of just, I mean, the overall idea of the next few slides is to compare blocking locking and non-blocking locking. There is such a thing as non-blocking locking, which means you sort of keep onto your thread until you succeed. So you don't do context switch or anything like that. And it looks like that. You sort of just, yeah, I don't even need to go through it. It's just compare and set and a bit of magic around it. Yeah. So, but the message here is that I mean, as I said, like earlier on already, you should worry about contention, not about locking. So even non-blocking locking can produce bad performance. Actually, sometimes worse than the locking kind of thing. Again, if you think about traffic, say the non-blocking locking thing is a roundabout, and the blocking bit is a traffic light. If there's high contention, then the traffic light is actually better in terms of throughput than the roundabout, because you sort of you're just messing up all the time. And non-blocking locking, it doesn't reduce contention; it just sort of postpones it a bit. That's the sort of main message here. Yeah, so these benchmarks are from Java Concurrency in practice. I just fudged the numbers a bit because I don't want to use the exact numbers for copyright reasons. But yeah, it's basically the same message. And also, like in general with concurrency, always measure what you're sort of expecting, because there's no general kind of theory. There's any advice I'm giving you, you might find an instance where it's not true what I'm saying. That's why you should always measure what you're actually seeing and don't assume stuff. So, how to reduce contention? The first, I mean, I'm not mentioning the sort of really basic approaches. The first bit advanced thing is lock splitting, which sort of arises if you don't write cohesive classes to begin with, which is like this thing where you have the server status, it keeps track of users and queries and uses the same lock for both collections, which is not necessary. You don't need to protect both collections with the same lock, and that's the sort of, yeah. I mean, maybe to take a step back again, lock contention is reduced primarily by accessing blocks fewer, or by reducing the granularity or the sort of duration you're holding that lock. So if you split it, it sort of just fits both requirements. And yeah, I say it's a bit advanced to do that, but it's actually not that sophisticated, because it only buys you a little time. If in this case load doubles, you're pretty much in the same situation where you were to begin with. So you can only, it doesn't scale. That's what lock striping is about. It sort of extends the idea from lock splitting, but works on sort of partitions of variable size data. And the sort of classic example for that is concurrent hash map, which just has 16 buckets with respective locks, rather than one global lock. Yeah, the thing about lock striping is it's sort of a bit of a trade-off between memory and performance. So for example, with concurrent hash map, you create these 16 buckets, but do you actually need 16 different buckets if you only have 2 CPUs? How likely is it that you're going to end up with 2 CPUs sort of interfering with each other? You can sort of configure that a bit differently as well. But yeah, so there's some things to keep in mind here. We kind of digged into details now already, at which point now I want to sort of take a step back again to sort of illustrate layers of synchronization. And this is from a talk from Jeremy Manson. There's a Google talk about the Java memory model, and I would highly recommend you to sort of watch that one as well to sort of get deeper understanding. I'm just going to cover the layers quickly. High-level concurrency abstraction is sort of the stuff you should start with. High-level is, relatively speaking, if you're used to Akka, then this stuff is pretty low-level already, but relatively high-level. Low-level locking, like synchronized and re-entrant lock, and then low-level primitives like volatiles and atomic classes, which you can use to implement non-blocking locking. So the next thing is that one thing that people sometimes don't know is that synchronization actually addresses two different concurrency issues. The one is the interference problem, the atomicity, which is the thing we know. And the other one is visibility, ordering, and memory consistency. That's the whole thing that volatile is about. So, for example, if you take this code and you sort of run this live or die method in two different threads, you all know that this is not thread safe, and you could either have, if you start with 0, you could have 1 or 2. But the thing about visibility is that you could actually have both 1 and 2. It just depends on the thread you're using to observe the value to see a different value. And that's a sort of really, really weird issue, which is why I call this a sort of Schrödinger's memory tricks.
What do you mean here? What volatile is about?
But volatile solves that, or volatile sort of deals primarily with visibility. It doesn't volatile doesn't solve any of the atomicity problems, but it solves the visibility and ordering problem. It's sort of it's a thing you can use to establish. I'm covering this later.
Okay, great. Yeah.
Okay, let's start with one example that looks perfectly thread safe. But there is an issue in here, and I'm asking you to spot that issue.
There is a typo on the comment.
Okay, yeah, no, that's not.
It's a
It's a double check locking implemented without volatile.
Yeah, exactly. And what is the issue about not doing that?
Yeah, the Java memory model permits that one thread it's a different value than the other thread.
Yeah.
Because of
exactly.
caching and optimization, it permits it.
Yeah. So, here it's not quite obvious what's wrong. Here it is a bit more obvious if you look at it. It's sort of the cache is assigned to the preloaded cache, the empty preloaded cache, and that's semantically exactly the same as the piece of code before, as the compiler and pretty much everything on your computer is allowed to sort of conspire against you and do this kind of stuff. So, and that's what volatile is about. Volatile sort of prohibits these kind of things, and it does something more, which is these happens before relationships. So you can solve this reordering if you clearly specify what needs to happen one after another. And this is, there are certain relationships defined, like the monitor lock rule. If you say you unlock a monitor somewhere, then everything you did before that unlock will be guaranteed, it's guaranteed to be visible after you lock that same monitor again. And the same applies to volatile as well. So if you write a volatile field, everything that you've written before that will be visible after you read the same volatile field. That's what this happens before a relationship is about. Okay? I mean, you don't need to grasp it in all its details to understand stuff later on, but it's just something to keep in mind. This is now sort of making use of this volatile kind of happens before a relationship, and it's a mini akka, more or less. I hope you can read the code, I'm not sure. It's by Victor Klang, and it sort of exemplifies volatile piggybacking. So, as I said, you can sort of, there's this happens before relationship which you can trust upon, and he made use of that here when he said, it sort of contains the basic methods again. You can enqueue messages, which will then be added to a sort of message box, and then this async method is called, which just checks if there's anything to process and if we should execute ourselves. And it does that by numbering certain atomic kind of things, which has the same semantics as volatile. So if you set this thing, it is like setting a volatile field, which means everything you did up until now, including this message box offer thing, will be visible to the thread later on, which happens in here. So you, in this run method, you check the same field again and see if it's been set to 1, which means we should be executing ourselves, and then we process that message. This, it's a sort of a fragile kind of application of the happens before relationship, but it guarantees that anything will be visible in that thread. Okay.
You can zoom on
If I can see it here, I don't mind. Yeah, this is another example of volatile piggybacking, or when it doesn't work. This is how thread pools are sort of implemented. The run work, but I guess that's too much of a detail here. Maybe we'll come back to it later if we have enough time. I'm just going to run over it. So the next thing, immutability. Immutability has its place in the Java memory model as well. In particular, the final keyword has 2 different semantics. The one semantic is you cannot assign anything to that field again. I mean, I'm just talking about fields, not final classes or anything like that. So that's the one semantic. And the other is anything that you set in the constructor is guaranteed to be visible by any other thread as well, if you construct it properly, which we'll see later on. Which is not the case for other fields. So for example, if you have this piece of code, and this is actually from the Java language specification, so I'm not making this up. And I'm not making anything else up either. So yeah, you initialize this instance. It just sets x to 3, y to 4, and then later on you read it somewhere. And the thing is, I is guaranteed to be free because x is final, but j could actually be 0. We don't know. It's a threading issue. It's not defined. Oh, and sorry. This is why if you're using actors, any message that you're sending should be immutable. And immutable according to that definition, because otherwise you might run into issues with regards to stale data. So the next thing is there is a proper definition of immutability in the Java language. Well, I'm not sure if it's in the Java language specification, but this is the sort of agreed upon definition. And it has these 3 conditions. Its state cannot be modified, it doesn't return anything that's mutable, it doesn't take anything that's mutable, it doesn't clone it, these kind of things. All fields are declared as final and is properly constructed, which means that this reference does not escape during construction. So if you have some kind of event listener, you don't say register this or whatever. You don't do this, otherwise it's not immutable, and you could run into thread issues again. And this goes back to what I was saying last time. Java, the string class is not immutable according to that definition. It doesn't matter though, because there are actually data races in the string class, but they're implemented in a way that they're benign, so they always produce the same result. The worst thing that could happen is that you calculate the hash code twice, or more often, but it's always going to be the same one, so it doesn't matter at all, but it's still worth knowing. Okay, now we're going to go a bit more high level. Tasks and thread pools. So the trouble with scheduling tasks is usually that developers are quite naughty in a way and write these dependent tasks and heterogeneous tasks which are difficult to schedule. So for example, if you take these 2 tasks and schedule them in parallel, you only achieve like 9% speed up. That's not even worth bothering. And the trouble with dependent tasks is if you have a thread pool with a fixed size of threads, you could run into deadlock issues. So for example, if one task depends upon another task finishing, but that task depends upon another task finishing, and so on, until you arrive at a task which is not even scheduled because the thread pool is exhausted. That's a deadlock issue, which, you know, it's not your fault in a way. I mean, you can argue about it, but yeah. So obviously you should break up tasks into small little pieces, and then there is the thing about configuring the thread pool. There's a lot of different sort of things you can do with thread pools, and I'm sure you know all of them. But one thing I'd like to sort of mention is the two last ones. That's sort of instances of a thread pool that come with no sort of predefined factoring method, but sometimes they're quite useful, and that's the one thing I'd like to sort of show, which is you configure a thread pool, or maybe I'll go back, it's easier to see it here. So you configure a thread pool, take this sort of second last. You configure the thread pool to be bounded in terms of threads, so you don't create arbitrarily many threads, just a fixed number at most, because you don't want to run out of memory or anything. I mean, it does introduce the deadlock issue, but we solve it differently. And in addition to that, we don't allow tasks to be unbounded either. So usually it's the case that you can submit as much as you want, and the queue just grows and grows and grows, and it doesn't ever sort of prohibit you from queuing anything else, unless you configure it differently. But the nice thing about this is that you can make use of what's called a saturation policy to offload work from your thread pool again. So if the thread pool is exhausted, you push tasks back to the client without the client knowing about it. So for example, I mean, this is what the caller runs policy says, that if I reject executing another task, it's the caller's responsibility to execute the task, which means ec.execute becomes synchronous. It executes that thing immediately. It doesn't queue anything, it executes it. And I know this seems like a weird thing, why would you want to do that? But it's actually a quite nice thing to have if you want to sort of handle degradation sort of a bit nicer in a way. You know, TCP starts dropping connections, and then the load balancer kicks in. You sort of don't drain requests that you can't handle anyway, so something else can take care in that case. Or another nice use case is asynchronous loggers. You know, usually if you're sort of developing performance critical applications, you want to offload the logging to a different thread. But the trouble is, when shit hits the fan, you do want those logging statements, because that's your only point to find out what went wrong. I mean, and that's usually things that coincide. So if there is some kind of issue with, if your application is about to crash, logging is most probably not going to work either if you're using asynchronous loggers. And that's just the worst thing that could happen. So asynchronous loggers, this kind of configuration, a match made in heaven. Okay, now we're going to come into sort of the section where we're talking about issues with thread pools. Now, as I said, you do want to execute tasks in a very granular way. Otherwise, you have to sort of scheduling issue again, dependent tasks and whatnot. So this is how your task queue looks like. And now I'll leave it to you again to spot the issue in this kind of configuration. I mean, can you think of anything that does cause troubles?
Making sure that every task is only assigned to one thread.
No, that's what the blocking queue takes care
sorry.
takes care of. Okay, well, I'm just going to solve it anyway. The issue is contention arising sort of at this point, because this is now being accessed very, very frequently. And I mean, you sort of could imagine more threads doing that if you're actually working on a sort of proper server. And then suddenly this becomes an actual point of contention. And the way to work around this is, again, you don't worry about locking. Locking is not the issue. It's the way you organize your data. I mean, think about it. Why do you have to have one queue for every single fucking message? That's just insane. And that's why we do this kind of thing. So we separate tasks and data for that task so that the task can be executed. That's sort of the task represents now the task queue for the threads, and the task in itself has another queue which starts processing these messages. This is not the Akka model yet though. I mean, it kind of looks similar. We're getting there, but we're not quite there yet. So again, sort of to reiterate, now instead of one big queue, we have one small queue with tasks, which is not an issue anymore, because they're not accessed as frequently. Tasks keep running for a prolonged period of time as well, because they themselves then go through message queues and iterate over a couple messages each time, so they sort of stay running a bit longer. And there's no single entire message queue anymore either. Each task has its own message queue. So this is an example of sort of linear kind of scaling. If we add more tasks, we separate the locking as well. So n tasks with a queue each means 1 over n in terms of load per queue. That's the kind of thing we're aiming for. And that's one big reason why Akka is so much faster. I mean, maybe you didn't quite grasp the difference yet. Just think about it this way. Which of these two methods would you rather implement? You know, enqueuing each message separately and sort of creating a runnable just for that message? Or would you create a runnable that just iterates over the whole list and prints that list? This is queuing everything to be executed directly. This is sort of separating between tasks and messages in a sort of very simplified way. And apart from that, you also sort of exploit other things like cache friendliness. You don't need to switch threads all that much. You know, the cache can remain where it is. Garbage collection friendliness, new objects don't span over multiple threads, and that kind of low level stuff. And yeah, so again, I'm not making any of this up. The people from Akka, they did a benchmark with thread pools and fork join pools. Fork join pools work in a sort of similar way. I mean, I'm not going into detail, but yeah, they organize tasks differently as well, and you can just see there's orders of magnitude of difference between them. So at this point already, it should be quite obvious why not to use thread pool in a sort of heavily contended application. And now one more thing. As I said, we didn't quite arrive at the Akka model yet. I mean, we do have sort of actors, if you call these tasks actors, with message queues. But Akka enforces that each actor is run at most once at any time instance of that queued in the task queue, and then you start processing messages concurrently, which is, I mean, it's not a big issue, but the reason why you don't want to do that is sort of missing commandment in scheduling things, which is don't execute two tasks if they're likely to use the same locks, because that's just bollocks. One of them has to wait. Either way, it's just useless to do that. And how do you know whether two tasks use the same locks? Well, it's a sort of an educated guess. If it's actually the same task in a way, so it's the same actor, it's very, very likely that the same actor is gonna use the same locks. So it would be pointless to run that actor in a different thread at the same time. And I think that's sort of another reason in terms of performance why you have that property of actors being run once only at a time. Conversely, the thing you should now keep in mind is that if you write actors, make sure that whatever lock they acquire exclusively, in the sense that no other actor ever attempts to acquire that lock as well. Otherwise, you should create a new actor which is responsible for doing whatever it needs to do with that lock, and then these two actors queue messages to that one, so that you don't sort of start switching around between threads again. Yeah, that's actually pretty much my entire presentation. We went through it quicker than I thought. I hope you sort of understand now there's devils in the detail, and there's a lot of things to worry about. But understanding these nitty-gritty kind of issues helps you to design scalable applications in the long run. And yeah, that's pretty much it. And if there's anything else you would like to know, just read this book. It's the Bible in terms of concurrency. So yeah, are there any questions? I mean, I just rushed through it, so I guess there's... Okay, well, then I have a question for you. Just to see whether you actually understood what I was saying.
Yeah.
Okay, so suppose I have the case that I see an issue where one of my actors needs to process an extraordinarily high amount of messages, and it just can't keep up with processing these messages. What would you do in that case? What's the kind of issue you're expecting, or how would you go about solving it?
You mean that the actor cannot process the messages faster than the message arrive?
Yeah, so
at the queue.
So suppose you have this kind of scenario, but there's one actor with like thousands of messages, and they just keep arriving faster than the actor can process them.
Yeah, you should escalate to the one who triggered the messages, right?
So you mean you start throttling, or
yeah,
you start slowing down
you should
senders?
Send something to the client or someone who.
Or implement some load. Okay, you have more instances of the same actor and load balancing.
Sorry,
and some kind of load balancing actor.
Okay, what does that actor then do?
Okay, it receives all the messages. Okay, sorry.
Yeah.
The same problem.
Yeah.
Okay.
You could also push back the load to the client to say we stop receiving messages and make a synchronous
Yeah.
process with this message.
Yeah, that's a good way to think about it. And yeah, I mean, I don't have any particular solution I'm advising you now either. I'm just asking, yeah. Okay, I'll just leave it at that then. Okay, thank you.